Hi, my name is Brian Caffo, and this is the two-group intervals lecture in the Statistical Inference Coursera class. This is part of our data science series. It's co-taught with my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so independent group T intervals. So now we're getting to the point where we can actually do things, right? Up till now, this class has been conceptual mostly, but now we're getting to the point where we can do things, right? Yeah, before we could create a confidence interval, but a confidence interval mostly for, one thing, right? It's comparing two groups of things. That's where the action's at. Science is comparative, right? Okay, so suppose we want to compare the mean blood pressure between two groups in a randomized trial, those who received treatment and those who received placebo. Seems important. We can't do a paired t-test because the groups are independent and they may have different sample sizes, so we need something to do. So now we're just going to present methods for comparing independent groups. We're going to go kind of fast because you know everything already, and we're just going to go through the formalities of how you derive the confidence interval really quickly, and then after this you can just execute it, but we just want to make sure you understand how we do it, but then extending beyond this should be really no problem for anyone. Okay, so we have some normal mu x sigma squared data, IID, and independent from them we have some normal mu y data, IID. I'm going to assume for the moment that the variances are the same, and that we know that the variances are the same. So let's let x bar, y bar, sx, sy be the means and standard deviations. So we can just use the facts that linear combinations of normals are again normal. We know that y bar minus x bar is also normal. We know that its mean is mu y minus mu x, and we know that its variance is sigma squared times 1 over nx plus 1 over ny. So, and if we want to estimate sigma squared, it makes sense that we would use both sets of data. But it also makes sense that we wouldn't, if there was 100 observations for x, if nx equals 100 and ny equals 10, then we would want to weight the sigma squared estimate from x more than the one from n. So look at this pool variance estimator, S sub p squared. It's nx minus 1 over nx minus 1 plus ny minus 1, okay, times sx squared, plus ny minus 1 over nx minus 1 plus ny minus 1 times sy squared, which is equal to p sx squared plus 1 minus pi sy squared. So again, it's a convex combination between the two variances, where if nx is large relative to y, pi will be close to 1, and if nx is small relative to ny, then 1 minus pi will be close to 1. So it's just an average of it's a generalized form of average between the two variances, and it'll be 1/2 for each if nx equals ny. So this pool variance is just an average between the two variances, where it weights whichever one has more data with more weight. Okay, so I just repeat these statements here. I repeat those statements there. The pool variance is unbiased because the individual ones are unbiased. You can just go through the steps right there. It's pretty easy. And it turns out the pool variance is independent of y bar minus x bar. We don't really cover that in this class, but so take my word for it. It's true. And then it's also true that take this pool variance estimator, multiply it by nx plus ny minus 2 over sigma squared. That works out to be nx minus 1 sx over sigma squared plus ny minus 1 sy over sigma squared. That's the sum of two independent chi-squareds, and it turns out that the sum of two independent chi-squareds is also chi-squared, and the degrees of freedom add, so it's degrees of freedom nx plus ny minus 2. So at any rate, the point being that this is a chi-squared, and hopefully you see, if you remember the T lecture where I'm going with this, that we're going to try and create a T statistic. So if we take this z statistic, y bar minus x bar minus mu x minus mu y, over its standard error of y bar minus x bar, the true standard error, not the estimated standard error, we know that that's normal. Both it's asymptotically normal, but also if the y's and the x's are individually normal, then this is exactly a normal distribution. But then if we divide this whole thing, I'm missing my divided by sign there, if we divide this whole thing by this guy, which we just said is chi squared, divided by its degrees of freedom, so square root of a chi squared divided by its degrees of freedom, we've taken a standard normal, right, and divided it by the square root of a chi squared divided by its degrees of freedom, and we wind up with this statistic, which we know has to follow a t distribution, because whenever we take a standard normal and divide it by an independent square root of a chi squared divided by its degrees of freedom, we get a t distribution. So this guy is distributed as a t, and notice it's just this formula with the standard error replaced by the estimated standard error, where the estimate is given by the pool variance estimate. Okay. So again, the form is estimator minus true value divided by standard error. Another thing I would make sure you remember whether you subtracted y bar minus x bar or x bar minus y bar. Save yourself some grief and keep track of that. Okay, so the confidence interval, so the confidence interval is just that guy, y bar minus x bar plus or minus the relevant t quantile times the standard error. Okay. So yeah, remember this interval is assuming a constant variance. If there's some doubt, we'll do what we discuss later. And in fact, you might as well just always assume there's a non-constant variance, so you don't lose so much. There's a function t.test for doing this, but not if you're just given summary values like this. So in this case, oral contraceptive users versus 21 controls, and they're looking at blood pressure, systolic blood pressures in milligrams of mercury. So here's the oral contraceptive users, here's the controls. It's 133 versus 127. Is that enough of a difference to say that oral contraceptive use appears to have some amount of, imply some amount of higher blood pressure than the controls? 15 versus 18 for the standard deviations. We can create the pooled variance estimate, and here I'm creating the pooled standard deviation estimate by square rooting it, but you can see the calculation there. And then we can create the confidence interval by subtracting the two means, add and subtracting the relevant t quantile times the standard error. We get our confidence interval for the difference in means between contraceptive users, where we subtracted oral contraceptive users minus controls, and we can see that 95% confidence interval for the difference in the population means between those two. We are checking whether or not this interval contains 0 because we're interested in whether oral contraceptive users have a higher blood pressure than controls. This interval is higher, more larger than 0 than smaller than 0, but the lower endpoint does dip below 0, and so we can't conclude that the oral contraceptive users have a higher mean than the controls, and that this difference could be attributed to chance. Okay. Here's the sleep data from Galton, which is the default example for the t-test in R. So here's my x1 and my x2 are from the two groups, my n1 and my n2, and then here's my pooled variance estimate. Here's my difference in means, where I subtracted group 1 minus group 2. The standard error of the mean is the pooled variance times square root 1 over n1 plus 1 over n2. Here's my confidence interval. I get this guy. No apparent difference. And then, of course, if you just do t.test, in this case, paired equals false, var equals true, it'll give you the same confidence interval. As a side note, if you read Galton's original paper, it says that the data are paired, and if you plot them, as far as I can tell, they appear to be paired. And there's a huge difference between treating things paired and treating things as independent, right? So if you treat them as independent, you're saying, I'm comparing this group and this group separately, and this point has no relationship with that point, right? So what you're looking at is this amount of variability versus this amount of variability, okay? And that amount of variability. Okay, but if you take the differences, right, what you're talking about is the amount of variability in these changes in heights. So if, as it appears to be the case in this data set, right, imagine if every one of these lines was perfectly parallel with the same slope, then the variance of the difference would actually be 0, right? So by ignoring the pairing, you'd have all this variation, but when you account for the fact that you have repeat measurements on subjects, you'd have no variation. And you have much less variation in this data set when you look at the pairing, right? The slopes of all these lines are, disregarding that guy, are all fairly consistent. So my point being, don't ignore pairing if you have pairing, because it's wrong, and B, you're using the wrong variance, but B, because in some cases you can actually reduce a lot of variance. Now that's not always the case, but sometimes you can. If there's a lot of correlation between the first and the second measurement, that happens. Let me also briefly say, if you have unequal variances, then the standard error is that guy, or the standard error of the difference in the means is that guy, right? And we no longer have a T statistic, by the way. But this statistic, where we replace the variances with their estimated values, it works out to kind of follow the T distribution, but the degrees of freedom are really funky, right? So here's those funky degrees of freedom. It's just a number you can plug into it, and there isn't a lot of intuition behind it. And I'll correct those slides. Notice this should be sx squared right there, and that should be sy squared right there. So we can redo our example, but there's no change as a matter of there isn't anything to change in our example other than the degrees of freedom and how you do the standard error calculation. But in R, you just set var equal to false, which is, I think, the default. Double check me on that, but I think it's the default. But when in the efficiency of this interval is pretty good, so you're not losing that much by just always assuming the variances are unequal, even if they're equal. So you might as well just always do var equal is false. So this is for the t-test. If you want to compare other kinds of group data, for binomial data, there's lots of ways to do it. We'll cover logistic regression, which in the regression class. And for count data, there's chi-square test and exact test. But we'll cover GLMs for doing that in the regression class. And then I would also say my other class, Bootcamp 2, covers lots of these special cases because they pop up a lot in biostatistics. I don't, they wouldn't maybe pop up as much in data science type settings, so we're not going to cover all these special cases. But in biostat, you see them pop up all the time.